In the previous video, we ended discussing solved examples in topic of current electricity, and today we are going to continue with a solved example. Figure below shows a circuit with two batteries in opposition. That means zimekuwa connected kwenye opposite to each other. One has an EMF of 6 volt and an internal resistance of 2 ampere, and the other has an EMF 4 volt and an internal resistance of. Calculate the PDF across the point XY. If we are connecting the voltmeter across XY, what will be the potential difference? So effective EMF itakuwa sawa na difference kati ya EMF wawili. Sababu huyu atakuwa anapeleka current, atakuwa anapeleka current kwenda direction hii, na huyu atakuwa anapeleka current kwenda direction hii. Lakini kwa sababu hii volt yake ni ndogo kuliko huyu, so finally volt ya huyu itamove kama, yani volt ya huyu itakuwa kubwa kuliko ya huyu. So the effective EMF will be 2 volt. But the total internal resistance itakuwa ni, you are just adding, because this arrangement of cells ni kama two resistors in series. So by adding you will get 10, and then finally V is equal to IR. So current I itakuwa sana hapo. So EMF atakuwa sawa, EMF1 itakuwa sana voltage XY plus VR1, that is EMF1. Na voltage XY ni sawa na EMF1 minus 0 pale. So EMF1 ni hapa, voltage atakuwa ni huyu hapa 0.2 times huyu current times resistance. So voltage XY itakuwa sana 6 minus hiyo hapa ambayo itakuwa sana 5.6. Alternative unaweza kutumia EMF2 na VR2 ile pale. So finally utakuja kupata 5.6 ambayo ni ile. So you can continue with the classification of materials, where we have 3 basic types of materials. Then insulators, ambao insulator huwa hapitishi kabisa umeme, and then we have semiconductor and the metals or conductors. So in electronics we discuss the classification of materials, and then we shall discuss what is the difference between these materials. We shall discuss what is different between insulators and the semiconductors and the metals in the internal structure. So there are those insulator, there are those whose electrical conductivity is negligible. So if they conduct electricity, the rate of conducting electricity is very small, almost negligible. Do not allow electric current or charges to flow through them. We shall discuss the reason behind in electronics that there is a very large gap between the valence band and the conduction band in these materials. So some few examples of insulators: we have glass, rubber, plastic, wood, etc. But from there we have semiconductors. These are materials whose electrical conductivity lies between that of insulator and metals. For example, here we have silicon, gallium material. All of these, most of the semiconductor, they are group 4 elements. But from there, we have metals, which we are discussing in this topic. They are metals. So metals, these are those materials whose electrical conductivity is very high, such as aluminum and the copper, etc. So we have many metals, we have iron and others, which allow the conduction of electricity through them. So these are those simply because they allow electric charges to flow one point to another. So hiyo materials classification tutaenda kuisoma in deep kwenye mambo ya electronics. Again, from there you can discuss the concept of resistivity of a material. Electrical resistance of a material depends on the following. Electrical resistance of a material depends on the length of the material, and this is direct proportional. If the length of the material increases, the resistance also increases. Also depends on the cross-sectional area. This is inversely proportional. If the cross-sectional area of the material increases, the resistance of a material decreases. But also depend on the nature of material, and then finally ni temperature. So nature of material ndo tunasema resistivity, na temperature iko temperature. So we are first looking at the relationship between resistance and the length cross-section with the nature of material. Then finally we shall discuss about the relationship between the resistance and temperature. So resistance of a material increases with increase in length. Also resistance of a material decrease if the cross-sectional area of the material tend to decrease. So deriving this, we would say resistance increases with the length, and then resistance decreases with cross-sectional area. So combining resistance will be increasing with length and decreasing with cross-sectional area. Removing the constant, the proportionality sign R, we'll put the constant of proportionality, which is resistivity, L divided by A. So resistivity will be equal to resistance A divided by length. That is how we are solving for the resistivity of the material. It is resistance times cross-section area divided by length of that materials given. So finally tutakuwa tuna resistance is equal to resistance is inversely proportional area direct proportional to length. Then resistance is equal to KL. K is the constant of proportionality, which is resistivity. So tunasema kwamba where K the proportionality constant called resistivity of the material. Resistivity of the material is just like the specific resistance of the material denoted by the symbol here for rho. We call it the rho symbol. So from the equation, resistivity will be equal to resistance times area divided by length. Now suppose area, length, and resistance are measured in meter square, then in length in meter and resistance in ohm, then you will have ohm meter. We'll have ohm meter as the SI unit of resistivity. SI unit of resistivity should be ohm meter. So resistivity of a material is the numerically equal to the resistance of a piece of a material or conductor when a conductor has cross-sectional area of 1 meter square and length of 1 meter. Cross-sectional area of 1 meter square and length of 1 meter. The relationship between resistivity and mobility of electron mu. So a current flowing in a conductor I, according to the electron theory, is given by I is equal to electron density E AVD. I hope you know about this. But we are saying that the drift velocity VD is equal to mobility of electron times electric field. Drift velocity is equal to mobility of electron times electric field. Substituting this here, then let's see how we will get it. So if you substitute, you will get current I is equal to NE A mu E. Then if you divide this equation with the area, you get current divided by area is equal to current density J, then NE mu E. But remember that the conductivity, current density J is equal to conductivity times C, electric field. But conductivity is equal to 1 divided by resistivity. That is to say, electric field divided by resistivity. So finally, electric field divided by resistivity is equal to NE mu E. So E with E will cancel, and then finally we'll get resistivity is equal to 1 divided by NE, which is electron density electric field times C mu. In the next session, we'll see the dependence of resistance on temperature, how resistance tend to vary with the temperature of the material, the dependence of resistance of material on temperature. Thank you.